Hello, good evening. So this is 11th physics class. We'll wait another 1 minute for another students to join. So can you hear my voice? क्या आप मेरी आवाज सुन सकते हैं? That's good. Hello Samir and hello Suraj. Nice to meet you. Okay, so we'll start about 11th physics lecture today. Let me present my screen. So let me know when you can see my screen. So can you see my screen? That's good. So we last time we started with laws of motion. So do you anyone has any question about this chapter, like what we discussed last time about kinematics, Aristotle fallacy, or Newton's laws of motion, which we started, right? So if you have any questions, please write in the chat box. I'll wait for 1 minute if you have any question. If not, then we will go ahead with other topics. So that's good. If you have no question, then I assume that you have understood everything. So let's go to the next thing. So this is we discuss about Newton's laws of motion, first law, second law, and third law. Uh, and we discussed about this second law, where how the momentum and mass acceleration is used for the force, right? So we will discuss more about importance of Newton's first law of motion. Okay, so this is why it is important about Newton's first law of motion. So we will see point by point. It shows it shows equivalence between state of the rest and state of uniform motion along a straight line, as both need a net unbalanced force to change the state. So what does it mean? इसका अर्थ क्या होता है कि न्यूटन्स फर्स्ट लॉ में हमने देखा था कि कोई भी बॉडी अगर उसी रेस्ट पोजीशन में है या यूनिफॉर्म मोशन विथ कांस्टेंट वेलोसिटी पोजीशन में, अगर उसे चेंज करना है तो हमें क्या, एक अनबैलेंस एक्सटर्नल फोर्स इज रिक्वायर्ड, राइट? So which we have discussed in the first law. Both these are referred as state of motion. So जो भी मतलब either body is at rest or it is at uniform motion, both are termed as state of motion. So motion की एक state है, either it can be a rest or it can be a constant velocity. So the distinct between the state of rest and uniform motion lies in the choice of frame of reference. Okay, so frame of reference हम आज पढ़ेंगे बहुत डिटेल्स में. So so what is mean by what is the difference between state of rest और यूनिफॉर्म मोशन? सो हमने लास्ट टाइम देखा था कि अगर एक प्लेटफॉर्म है और प्लेटफॉर्म के बाजू में ट्रेन है, this drawings may not be so good, but I will try to make some good drawings maybe in next lectures. So if this train is moving and this platform is here, right? platform can't move. This is platform, right? Sorry. So this is platform, and this is the train. So we know that this is at rest and this is at motion, right? So what choice we have taken right now? If frame of reference, we have taken that we are standing at the uh, platform. So हम platform पे खड़े हैं, तो what we can see is train is moving, train is in motion. अगर हम ट्रेन में बैठे हैं तो what we will see that हमें ट्रेन में बैठे तो हमें लगेगा कि ट्रेन is steady and platform is moving, right? So it is always what choice what we make from the frame of reference, right? That's what the main that's what this sentence says, that whether that body is in motion or in at the rest, that we can decide from the frame of reference what we are taking as a frame of reference. Hopefully you're cleared about this frame of reference. Now second thing, like about the first law of motion, we have seen that one is frame of reference and it defines the state of motion. Then second, what is the importance of first law of motion? It defines force as entity or physical quantity that brings about a change in the state of motion of body. That is, force is something that initiates a motion or controls a motion. Second law gives a quantitative understanding or its mathematical expression. So there is force, right? So एक फोर्स जो एंटिटी है जो हमें बताती है कि whether means that will bring the change in a state of motion. अगर जो state of motion है उसको change करना है तो हमें क्या करना है? एक फोर्स चाहिए होता है, या जो फोर्स होता है वो हम क्वांटिफाई कर सकते हैं. हम ऐसे नहीं कहेंगे कि या वो बॉडी इज इन मोशन, उसका चेंज हो गया स्टेट ऑफ मोशन बिकॉज सम फोर्स, राइट? और बिकॉज समथिंग एक्स वाई जी, नो. सो देयर इज सम फोर्स, वी कैन क्वांटिफाई दैट कि इतना फोर्स चेंज हुआ इसलिए इतने उसका मोशन जो है या स्टेट ऑफ मोशन उतना चेंज हो गया, वो हम बता सकते हैं बिकॉज ऑफ दिस फोर्स. ओके, सो वेन एवर देर इज फोर्स देर विल बी स्टेट ऑफ मोशन चेंज होगा, और वो फोर्स हम लोग क्वांटिफाई कर सकते हैं, उसका हम लोग रिलेशन बना सकते हैं. ओके, सो फोर्स इज वेरी नेसेसरी टर्म हियर. देन वी विल it defines inertia. So again another importance क्या है फर्स्ट लॉ का कि inertia as a fundamental property of physical object by which object resists any change in state of motion. So inertia एक चीज है जो हमेशा रजिस्ट करती है चेंज ऑफ मोशन को. मतलब सपोज दिस इज अ ट्रेन, राइट? और so train is moving at velocity v, और इस ट्रेन का जो वेट है या उसका मास है वो है m. ओके, सो अगर ये इस तरह से चेंज मतलब इट इज इन कांस्टेंट वेलोसिटी v. ओके, और हमें उसको चेंज करना है, मतलब अभी वेलोसिटी इज 50 किलोमीटर पर आवर है and we want to change it to 60 kilometer per hour, right? So we can make a force, उससे ये चेंज हो जाएगी, बट देर इज सम inertia, it is which resists this change, right? So ये जो बॉडी है उसका एक खुद एक inertia होता है, उसके कारण वो चेंज नहीं होगी. तो वो हमें inertia के रूप में दिखाई देता है. सो हमें अगर 50 to 60 किलोमीटर चेंज भी करना है तो जो inertia है इट ऑलवेज अपोजेस, राइट? वो हमें चेंज नहीं करने देता. सो inertia इज मेजर्ड एज, तो inertia कैसे मेजर करते हैं? एज अ in terms of mass of object, right? तो more specifically it is called as inertial mass. इसको क्या कहते हैं? Inertial mass, which is ratio of net force to the corresponding acceleration. So इसका मतलब क्या है? ये हो गया हमारा मास, इनर्शियल मास, जो ऑलवेज चेंज करता है. सो अभी जो भी कार, मतलब अभी जो ट्रेन का मास है, सो दैट इज कॉल्ड 1000 kg है. सो दैट ऑलवेज अपोजेस टू मेक दिस चेंजेस, राइट, टू द एक्सेलरेट. सो हमें फोर्स लगाना है. फोर्स इज, ये हमने देखा था, मास इनटू एक्सेलरेशन. सो मास यहाँ क्या है? कांस्टेंट है, राइट? मास कांस्टेंट है. सो दिस इज कॉल्ड inertial mass also, right, which opposes to the change, like this acceleration is change. So ये change करने के लिए ये जो mass है वो oppose करता है. इसके लिए this is called inertial mass. Okay, hopefully आपको ये inertial mass और इसका कुछ fundamental समझ में आए होंगे. If you have any doubt, please let me know. So this is importance of first law of first law of motion. हम देखते हैं what is the importance of second law. Second law में क्या होता है? It provides a mathematical formulation for measure of force, right? So हमने देखा था last time कि force is nothing but rate of change of linear momentum, right? ये है formula उसका. Force is nothing but measure of rate of change of linear momentum. तो यहाँ देख सकते हैं P is termed as momentum. So hope you know that generally जो भी first letter होता है किसी भी uh, किसी भी वेरिएबल का, तो वो हम लोग यूज करते हैं एज ए वेरिएबल, राइट? जो भी क्वांटिटी है, जैसे मोमेंटम, वेलोसिटी. वेलोसिटी तो हम v यूज करते हैं, but यहाँ p यूज किया गया. There may be some different reason because m already used for the mass, right? So they don't want to confuse between these two. So they are using p as a momentum. So यहाँ देख सकते हैं dp by dt. So what is meant by that? dp by dt मतलब change in momentum, right? Change in momentum divided by change in time. सो चेंज इन टाइम मतलब जो भी है, जैसे मोमेंटम 5 से 10 हो गया, सो व्हाट इज द चेंज? 5 - 10, राइट? और चेंज इन टाइम, टाइम कितने से चेंज हो रहा है? 5 सेकेंड to 10 सेकेंड, मतलब इसके डिफरेंस कितना है? 5, राइट? सो इस प्रकार से जो भी चेंज है वो अगर न्यूमरेटर में लिखेंगे और डिनोमिनेटर में उसका टाइम लिखेंगे, कितने टाइम में उतना चेंज हो रहा है, तो वी विल गेट द फोर्स, राइट? सो हमने देखा था force is equal to ma, but it is applicable whenever there is constant mass. So let's derive this quantity first. dp by dt. So dp by dt is d, और हमें पता है p मतलब क्या है? mv, right? That is mass into velocity. So derivative of mass into velocity divided by derivative of t, right? So अगर हम लोग इसको, we know this associative law, right? So we have to take one quantity first, we have to take derivative, then we have to take another second quantity. So first quantity we have taken as mass here, dm by dt, and here v as a second quantity, we have taken the derivative. So by this associative law, we got this formulation, right? dm by dt into v plus m into dv by dt. So यहाँ देख सकते हैं हम लोग, this is first and this is second quantity, we have taken its derivative successively. So so dv by dt क्या होता है? Change in velocity divided by change in time, what it's become, dv by dt is nothing but acceleration. So वो हमने यहाँ substitute किया. So we know the formula, like f is equal to nothing but dm by dt v plus ma. So यहाँ देखेंगे तो for a given body, if mass is constant, so अगर कोई भी चीज कांस्टेंट है तो वो क्या होगी, विद रिस्पेक्ट टू टाइम चेंज नहीं होगी. तो ये क्या होगा, जीरो होगा, राइट. dm by dt becomes zero. So we know there is, with respect to time, there is no change, then it becomes zero, right. So then in that case, f becomes mass into acceleration. In the case of rocket, both the terms, right, are needed as a both mass and velocity varying. So जो रॉकेट है वो उसके बारे में मैं बताऊंगा कि जो रॉकेट है, so whenever it goes in the space, what happens, there is fuel, right, it burns and it propels inside in a vertical direction, right. So ये जो fuel होता है, so rocket carries this fuel, right. So this fuel is in very huge quantity. So जैसे जैसे ये स्पेस की तरफ बढ़ेगा रॉकेट, so this mass of this rocket changes, right. So in that case, this f is means f we have to derive in terms of where the change in mass is also occurs and velocity is also changing. So we have to take this formula for whole formula for carrying calculating the force. So हमारी जो कार होती है उसमें भी फ्यूल होता है, राइट. सो वो फ्यूल भी धीरे धीरे क्या होता है कि it burns, right. So whenever our car is moving in x direction or y direction, so force भी जब हम फोर्स कैलकुलेट करेंगे किसी भी कार के लिए भी, right, this is a car, right, car or bus, anything, or you all may be using scooty or this bikes. So this has the fuel, right. Whenever you are driving towards one direction, there is a fuel tank. It loses its fuel, right. It burns fuel to accelerate this bike or car or vehicle. Then we can use this formula where the mass and velocity both the changes. So yeah, hopefully you got this momentum, change in momentum and change in force. So what is the second importance for the second law? Another thing, it defines momentum instead of velocity as a fundamental quantity related to motion. What is changed by the force is momentum and not necessarily velocity. So ये क्या है? This gives us another thing like momentum. We are not defining the velocity, right? अभी हमने देखा कि एक मतलब जो व्हीकल है उस पे अगर हम फोर्स लगाएंगे F, so it should change the velocity, right? It may change or it may not change, but if we want to calculate the force in terms of change in momentum, we may need, we are not defining in terms of velocity, we are defining in terms of mass into velocity, that is momentum. So why we are defining in the mass into velocity? Because sometimes if we are applying the force, but there will be no change in the velocity, right. So in that case we may have to think in different direction, or we have to see, we have to quantify force for the different terms itself. So hence we are defining the momentum here, not only velocity. और हम लोग ये सब कहाँ से हमें पता चला? तो because of this second law of motion, right. And then Aristotle fallacy is overcome by the considering resultant unbalanced force. So एरिस्टोटल ने जो कहा था तो वो हम यहाँ ये उनकी fallacy is overcome by the some unbalanced forces. So there are whenever it is in that state of motion, it changes by some unbalanced forces, right? So which we can define here in the second law of motion. So importance, another importance of the Newton's third law of motion. So it defines action and reaction as a pair of equal and opposite forces acting along the same line. So ये जो third law है वो क्या बताता है कि there are equal and opposite forces and they are in the same line of action. So ये जो line of action है वो same होती है. ये न्यूटन्स थर्ड लॉ ऑफ मोशन बताता है. So action and reaction forces are always on different objects, right? So हम लोग अगर फोर्स अप्लाई कर रहे हैं तो एक बॉडी होगी और जो फोर्स रिएक्शन होगा वो डिफरेंट बॉडी से प्रोड्यूस होके आएगा. सो देयर इट इज ऑलवेज ऑन टू डिफरेंट ऑब्जेक्ट्स. सो इस प्रकार से तीन डिफरेंट लॉज है और उनके तीन इंपॉर्टेंस यहाँ बताए गए हैं. तो हम कुछ कॉन्सिक्वेंसेस समझ के लेते हैं. So what is the consequences? So action force action force exerted by body X on the body Y, conventionally written as Fyx, as the force experienced by Y. As a result, body Y exerts reaction force Fxy. In this case, body X experiences the force Fxy, while the body Y experiences the force Fyx only. Okay, so let's put into the figures or some objects so that we will understand that what is happening. So see that body X, right? This is body X and it exert force on body Y. This is body Y. So what is happening here? So there is force called F by body X. Action force exerted by body X on body Y, conventionally termed as Fyx, right? और जो बॉडी Y से जो रिएक्शन आएगा वो क्या टर्म होगा? Fxy. Okay, so these both are equal and opposite and in the same line of action में apply होंगे, right? So यही बताना चाहते हैं. ये दोनों मतलब this is a thing and this will be applied across this face, right? This force will be applied across this force. So what is the consequences of this third law of motion, that forces Fyx, Fxy and Fyx are equal in magnitude and opposite in direction, but there is no question of cancellation of these forces as those are experienced by different objects, right? So हम लोग इनको कैंसिल नहीं करना चाहिए कि हाँ ये दोनों इक्वल एंड अपोजिट है तो ये दोनों सेम हो गए और हम इसको अभी कंसिडर नहीं करेंगे. दैट्स नॉट द केस, राइट? सो ईच बॉडी इज एक्सपीरियंसिंग सम फोर्स, सो वी हैव टू कंसिडर while calculating the forces on the body. So I don't know whether you have come across this term like free body diagram. So in this free body diagram, this will be useful term and we have to consider this type of forces. So we can't cancel it out directly because each forces are experienced by the different objects. So that's what we are learning here about this Newton's third law of motion, and we will utilize this or we implement in these free body diagrams. Okay. So forces fxy and fyx, right? So there are two different bodies and they are exerting some force, and there is another reaction, right? When one body is exerting force and another is producing reaction to that force, right? So this always happens, but this need not to be in contact, right? This type of action and reaction forces need not. So we have seen that here they are contacting each other, but there are some forces, repulsive forces between two magnets. This we have observed that when two magnets come together, this is north side of both, right? So they will try to retract from each other. So this is called repulsive forces. So these repulsive forces are equal and opposite direction, but and this is classical case of action and reaction forces, but they are not in contact as we can see here, right? It is not in contact like this, these two objects. In this case, the two magnets are not in contact. Another force is like gravitational force between Earth and the Moon, or between Earth and Sun, are also similar pairs of non-contact action and reaction forces. Okay. So if you have any doubt, you can ask me in the chat box about this action reaction uh, and about anything. Okay, that's good. If you do not have any question, so let's move to the next example. So this is a very good example they have shown here. Sorry. So this is one example. So here we can see the hose pipe used for gardening is ejecting water horizontally at the rate of 0.5 meter per second. Area of the bore of the pipe is 10 centimeters square. Calculate the force applied by the gardener to hold the pipe horizontally stationary. So what is happening here? You might have seen the pipes in gardening area or anywhere. So there is water coming out of it at 0.5 meter per second, right? And the area cross sectional area, it is called area of the bore. So this pipe, so area is 10 centimeters square, right? So this is area of pipe. I'm just showing you. Okay, I think we'll make another good drawing. So this is the pipe, and from this is the cross sectional area. So this area they have given it as 10 centimeters square, and from it there is water coming out of at 0.5 meter per second. Okay. Calculate the force applied by the gardener to hold. So uh, if this is if this water is coming out of this pipe, then we have to hold this pipe, right? Otherwise it will move here and there. So how to calculate those force applied on the this hose pipe? So if ejecting water horizontally is considered as action force on the water exerts a backward force called recoil force on the pipe. So whenever this water is moving out of this pipe, it exerts means this is action force, and there will be a reactions happening on the pipe. That's why it is like it will be pushed backward, right? So there are two forces. Uh, One force is by this water when it is coming out of this pipe, and due to that force there is a reaction force, right? So if we calculate this action force by the water, then we can easily carry out the reaction force, because those are equal and opposite in the direction. So what is that force? So we know that F is nothing but dp by dt, and we have derived this formula for the force. Let me take here. We know that as v, velocity of ejected water is a constant, right? Velocity is not changing, it is constant. So that's why one term will vanish, right? So there will be only dm by dtv, where dm by dt rate at which mass of water ejected by the pipe. As the force in the direction of velocity is horizontal, we can use scalars, right? We know that only horizontal directions. We do not have to consider vertical or any other directions. So what is dm by dt? Dm by dt is nothing but d v rho by dt, because mass, right? Mass is, what is mass here? That is water, right? Rho into v, right? Volume of water ejected, and rho is v is volume of water ejected, a is the cross sectional area, rho is the density of water, and length of water ejected in time t. So we dm by dt, if we want to calculate, we are deriving in terms of volume into rho, right? Volume into rho becomes mass. So this volume we can further divide as a area into length. Area is the cross sectional area of the pipe. So this way we can carry out like area into rho is area, it's constant, right? We are not changing the area. And rho is the density of water. So density of water is also not changing. So that's why with respect to time, right? With respect to time, it is not changing. So we can take it out of the this bracket. And now what is remaining is dl by dt. So length of water is that which is changing, right? So what is meant by length? If length of water changing with the time is nothing but velocity, right? So this is the formula if we want to calculate the change in the mass of the water with respect to time. So we can calculate here by putting into the formula like dm by dt v. Uh, this v means a rho v. So a rho v square, and we can calculate the force applied by the this water ejected. So that is 0.25 Newton. So same force we have to apply here to hold this pipe. Otherwise, it will go here and there. So now we have calculated the force required by the uh, person to hold that pipe. So I will ask question. If you do not have any question, if you have any question, please ask in the chat box. If there is a no question, I will ask the question. So here we have to hold this pipe. हमें इस pipe को hold करना पड़ता है, right? With the hand, with or some retainers. So we might have seen in the garden also. So if we start the wall, and water starts flowing, then this pipe, go here and there. We can't hold that properly. That's we have seen. So sometimes what happens, this pipe is there, and we do not have to hold, right? It is like sometimes in garden we might have seen that it is lying there, water is coming out of that. So what is the reason that we do not have to hold that pipe? Can you tell me in the chat box? So here we have to hold, and we have to apply the 0.25 Newton force, right? But sometimes that pipe is lying in the garden, and we have started the water also, and water is flowing through that pipe, but no one is holding that pipe, right? It is not always there is someone holding the pipe. It is kept in that garden, and water is flowing through that. So what can be the reason why no one has to hold that pipe? Any answer from your side? It is general observation we have seen in any gardening area. So that is a very good observation. But again, this pipe, we also can keep it at the ground, right? But this pipe, we need something to hold here in on the ground also. But this pipe, we do not need anything. What possible reason? I'm just asking you. How gravity will affect here? Because gravity is affecting here also, right? In this case, but we have to hold this pipe. So again, why we have to hold this pipe? This pipe, because we are having the more force due to this water jet, right? So if this water jet is not substantially high, then in that case we may not need to hold this pipe, right? That may be the one reason. So uh, what we can do, so we can see that force is nothing but rho av square. So in that case we can see that force is directly proportional to the v square. Means if we change the velocity by half, it will change the force by uh, means square the magnitude, right? So what I want to say that if we change velocity from zero point 0.5 to 0.25, the force will change by fourth of magnitude. So what will be the force here then? Like 0.0625, right? So it will be fourth time. So what we have to do, we have to change the velocity in a such a way that this pipe itself will sustain that force. It doesn't need. So we have to reduce the velocity. That's the possible reason. Or we can make this pipe so strong that it can take this 0.25 Newton uh, force, right? So these are the two possible ways where generally we do in the practical applications. If you can come up with another idea to hold this pipe, then that will be another patent, we can say, or another good idea, right? So that will be innovation. So yeah, so any question here about this holding the pipe? If you don't want to hold, then we have to reduce the velocity, right? Or we may have to take a pipe so strong. So instead of this plastic pipe, if we use a steel pipe, then yeah, it can hold a better. It can, we don't have to hold in hand, right? It can lie on the ground, because we have seen the pipe network where we are getting the water to the tap. No one is holding that pipe. Yeah, means we have to retain that pipe in certain position. So we use some clips और we use some fixtures. वहाँ सब कुछ fixtures भी use होते हैं, तो वो steel pipe में भी force apply होते हैं, but that is in different way. uh, okay, so let's move to the next thing, that is inertial frame and non-inertial frames. Okay, so I will read first, then we can discuss. Consider yourself standing on a railway platform or a bus stand, and you see a train or bus is moving, right? According to you, the train or bus is moving or is in motion, right? As per your experience of the passenger in a train or bus, they are at a rest and you are moving. So whoever sits in the bus or train, they think that you are moving in backward direction. That's we have observed. Hence, motion itself is a relative concept. Hence, it's very important thing that motion always in a relative concept. We can't say that it's absolute term, right? It is always relative. To know a described motion, you need to describe or define some reference. If you want to describe the motion, you have to describe the reference. So, uh, suppose, sorry. So suppose one car is moving at 50 meter per second here, 50 kilometer per hour, sorry. Okay. So that's the velocity. And here is, we are taking, how can we say that it is moving at 50 kilometer per hour? How can we say 50 kilometer per hour? Because we take this ground as a reference, right? So with reference to ground, it is moving at the speed of 50 kilometer per hour. So whether we are right in this case, because we have to take a reference uh, which is not moving, or it is relatively right. So we are thinking that this reference is uh, con- uh, it's steady. It is not in motion. So whatever we are taking, is it right? So we are moving on the car or scooter or bike, right? So it is always shows some speed like 50 kilometer per hour. So that speed is with reference to this ground. Okay. So whether that speed is uh, it's related to that ground. So whether this ground is constant, we are taking this ground as a constant, right? Generally, if we take that earth, right? Earth is in also motion. So this ground is also moving in the space as such. But for practical, all the applications, what we take, this earth is steady. Okay. So that's the main concept. And here, that though this earth is moving at some certain speed, we are not considering that speed for calculation of the speed of the any vehicle. Okay. So we are considering this uh, ground as a reference which is not in motion, but actually it is in motion. Okay. So this is always an relative concept. That's what motion always called as relative concept. Everything is moving, so we have to see that one is moving, then other is also moving, right? So we have to take one as a steady, and we have to calculate according to that another uh, speed or another motion. So to know the describe a motion, you need to describe or define some reference. So here we are taking reference as a ground. Such a reference is called frame of reference. So this is called frame of reference. We are taking ground as a frame of reference, right? In this example described above, if you consider the platform, so here, if we consider the platform as a reference, then passenger and train are moving, right? If we consider this as a reference, frame of reference, then this as a we think that whatever in the bus, whoever are there, these passengers and bus are moving. However, if the train is considered as a reference, then if here, like if train or bus is considered as a frame of reference, then this platform and platform is moving, right? So whenever we whatever the frame of reference, we have to consider that we are into that, so it will give us a better idea. So if we keep if we are inside the bus or train, we can see that everything is moving backward, right? So this is called then we if we take bus or train as a frame of reference, then everything going backward, or everything other things which are on the platform, which we see as a moving backward. So that we see as a motion. So usually a set of coordinates with a suitable origin is enough to describe a frame of reference. So set of coordinates. So we know that X, Y, Z coordinates we use for the positioning of any object in this three-dimensional space around us. So we use this coordinate system. Those are enough actually to describe the frame of reference. If the position coordinates of an object are continuously changing with the time in frame of reference, then the object is in motion. So if suppose object is here, right, in the in this three-dimensional space, and if it is moving from one position to another position, it's changing its position, right? The time in frame of in this frame of reference, it is changing. The object is in the so if position coordinates of an object are continuously changing with the time in a frame of reference, then that object is in motion. So this object is called is in motion. Any frame of reference in which Newton's laws of motion is applicable is called, in simple understanding, is inertial frame of reference. So So in whichever the frame of reference you apply, right? If all the Newton's laws are applicable there, then it is called inertial frame of reference, any frame of reference, okay? It means if there is no net force, there is no acceleration. Thus, in an inertial frame, a body will move with a constant velocity, which may be zero. Also, if there is no net force acting upon it, in the absence of net force, if an object suffers an acceleration, that frame of reference is not inertial frame and is called non-inertial frame of reference. So what does it mean? So let's look one by one. So in inertial frame of reference, what does it mean? If there is no net force, there is no acceleration. So we have seen that through first law of motion, that if a body is in the state of rest, it will be in that state, or if it is in state of motion, it will continue to in that motion till we apply some unbalanced force on that body. So the same law apply here. So in this inertial frame, body will move with constant velocity. Thus, in inertial frame, right? This is inertial frame where the there is no it will move with constant velocity, right? Or it will be in the rest in this inertial frame of reference, unless there is some unless there is some uh, force is applied, right? So here they have mentioned about non-inertial frame. So we will discuss about that later. But let's understand the inertial frame of reference now. So suppose there is a vehicle and there are some passengers, right? So in this vehicle, we can see that if it is moving with velocity v, right? And if it is moving with velocity v, and this, if we take this as inertial frame, which are the frame of reference we take? Like suppose if we are taking the frame of reference as this vehicle itself. So vehicle is frame of reference. Whether that is inertial frame of reference or not, how can we decide? So it is in motion at constant velocity, right? And suppose uh, this driver in the vehicle presses accelerator, it applies the force, right? Then we change the velocity. So we know that this driver has applied the force and it changed the velocity, right? So this is called, and we know these laws, right? So this is called inertial frame of reference, where we know that due to this force, velocity had changed. We can uh, correlate this force and acceleration. So this is called inertial frame of reference, where we can apply the Newton's law of motion. But see the second sentence where it shows that in the absence of net force, if an object suffers an acceleration, that frame of reference is not inertial frame, is called non-inertial frame of reference. So, so here what we are considering, we have changed the velocity and we know that we have applied the force F. But here what happens, the person, if we apply the brake or if there is sudden acceleration, this person moves ahead or backward, right? So if we know that if in the bus or train, if suddenly there is brake applied, then we go forward, we lean forward, right? So these type of things, we don't know that no one has applied force on us, right? If we are sitting inside the bus or inside the vehicle and suddenly there is brake, then we go forward and we don't know anyone has applied force. No, right? So there is, we can't define such type of things here. So that is called non-inertial frame of reference. So we don't know that force. So means we know that F is equal to mass into acceleration, but what force is applied here? That is, there is some force which we can't quantify. In such case, it becomes non-inertial frame of reference. So if we want to consider the motion of passengers, then it becomes non-inertial frame of reference. Okay, hopefully you got this principle where what is meant by inertial frame of reference and non-inertial frame of reference. For simplicity, मैं ये बताना चाहूंगा कि जहां भी न्यूटन्स लॉ ऑफ मोशन से अप्लाई होते हैं वो इनर्शियल फ्रेम है, और जहां न्यूटन्स लॉ ऑफ मोशन अप्लाई नहीं होते, that is non-inertial frame of reference. We can't define the why this acceleration happening. जब हम बैठे रहते हैं या हम व्हीकल में बैठे हैं या बस में बैठे हैं एंड बस इज टेकिंग टर्न या शार्प टर्न, देन वी मतलब अगर लेफ्ट में टर्न ले रही है, राइट, कार, तो हम राइट में मूव हो जाते हैं. क्यों मूव होते हैं हमें पता नहीं चलता, राइट? देयर इज सम फोर्स. एनीवन हैज अप्लाइड फोर्स ऑन यू? नो, देयर इज नो सच फोर्स इज अप्लाइड ऑन यू. आपको किसी ने ढकेला नहीं है कि आप राइट में जाओ करके. this is just we can't define in terms of Newton's law of motion. Hence it is अगर हमें कंसिडर करना है कि हम बस में बैठे हैं और हम ऐसे अचानक बस लेफ्ट में जा रही है लेकिन हम राइट में जा रहे हैं, सो इन दैट केस इट बिकम्स नॉन इनर्शियल फ्रेम ऑफ रेफरेंस. ओके, लेकिन अगर बस ड्राइवर का हमें सिर्फ ओवरऑल बस का पोजीशन देखना है, बस ड्राइवर अगर एक्सीलेटर पे पांव दबाते हैं तो बस बहुत आगे चली जाती है और बस मूव होती है, उनका स्पीड बढ़ता है या स्पीड कम होता है, जो भी है वो सब हम कंसिडर कर सकते हैं इनर्शियल फ्रेम ऑफ रेफरेंस में. उसमें हम एक पर्सन या पैसेंजर को कंसिडर नहीं कर रहे. Okay, so what we are considering according to that, it becomes inertial frame of reference or non-inertial frame of reference. Okay, so let's move ahead. So measurement in one inertial frame can be converted to measurement in another inertial frame. So हमारे जो measurement है, जैसे हमने देखा कि ground पे बैठे थे या पैसेंजर जो ट्रेन में बैठे हैं, वो अलग अलग फ्रेम ऑफ रेफरेंस है, बट दोनों इनर्शियल फ्रेम ऑफ रेफरेंस है, तो हम उनको ट्रांसफॉर्मेशन कर सकते हैं. ओके, बाय सम वेलोसिटी वेक्टर्स वी कैन change those stuff. So illustration, so they have given small example. Imagine yourself inside a car, all windows opaque so that you cannot see anything outside. Also consider that there is pendulum tied inside the car and not set into the oscillation. So pendulum is also steady. If the car just starts in the motion with reference to outside or ground, just starts, okay, you will experience a jerk. At the initial moment, we will have the jerk. Acceleration inside a car, even though there is no force acting upon you, no one is there is no force acting upon you, but then also you are getting a jerk. During this time, the string of pendulum may be steady, uh, but not vertical, right? It may be steady string, but it is not vertical, it is also in some different position. During time of acceleration, now here it changes, right? This is second scenario. During time of acceleration, the car can be considered non-inertial frame of reference. So during this time of acceleration, whenever we are trying to start the car, we are just accelerating and we will get this jerk, right? So that jerk can be considered as a non-inertial frame of reference. Later, so here we will consider another case later on. Whenever it is smooth ride, right? Whenever there is no acceleration, we are steadily uh, put our put our foot on the pedal, and car is moving with constant velocity. There is no problem and no jerk, no problems, no problems to the passenger, right? Whoever sitting inside the car. In if the car is moving with the constant velocity with reference to ground, again, yeah, we are taking a reference as the ground, you will not experience any jerky motion, right? Yeah, I know there are some potholes and those stuff. We are not considering, we are considering very smooth road, right? And there is no such jerky motion is applied to the U. Then this is considered in the inertial frame of reference, right? So though we are sitting inside the car, we can see two frame of reference. One is inertial and one is non-inertial. So when to apply non-inertials, you know now, right? Whenever there is a no, we can't define which forces are applied on the means we can't define the forces and motion, then it is called non-inertial frame of reference, like in the acceleration at the start. Okay. Uh, so yeah, in the second case, whenever it is moving at the constant velocity, there will be it will be vertical and non-oscillating. So these are the two things. Okay. Uh, so I think time is up. So we will stop the lecture here. We'll see next time. Thank you.